Diagonalization. So if you think about a lot of the things we've done in this course, one sort of reoccurring theme is this theme of matrix factorizations. So it's often a case that a concept that we learn manifests itself as a matrix factorization. This is how the Gauss-Jordan algorithm manifests itself, which is as EA equals R. Forward elimination of matrices manifests itself in PA equals LU. The Graham-Schmidt algorithm manifests itself as A equals QR. But one thing that we haven't touched on in terms of relating it to a matrix factorization is eigenvalues. And this is the concept of diagonalization. So let's jump in here. Before we understand what diagonalization means, we need to understand what similar matrices are. So when mathematicians say that two matrices are similar, they mean something very specific. We say that a matrix A is similar to a matrix B if A can be written as a non-singular matrix X times B times the inverse of that matrix X. So to say that A is similar to B is to say that A is equal to X times B times X inverse for some X. Here's an example. Here we have an equation involving four 4x4 matrices. On the left here we have a matrix, let's call it A. And on the right we have the product of three matrices. Let's call this middle matrix B. And it turns out that the other two matrices are a matrix X and its inverse. So this is an example of similar matrices. And this equation is communicating that A is similar to B here. Notationally, it's convenient sometimes to use shorthand. So we write A tilde B to indicate that A and B are similar. So remember, when we say that two matrices are similar, we mean something extremely specific. This isn't vague language. This is completely unambiguous. Now, why do people care about similar matrices? Well, it turns out that similar matrices have a lot in common. They're not identical, but they have a lot in common. For example, if A is similar to B, then A and B have the same rank. They also have the same characteristic polynomial. And if you think about it, the characteristic polynomial encodes a lot of important information relevant to a matrix. Since A and B have the same characteristic polynomial, they'll have the same trace. They'll have the same determinant. They'll also have the same eigenvalues because the eigenvalues of a matrix are the roots of the characteristic polynomial. Each eigenvalue of these two matrices will share an algebraic multiplicity because these two matrices have the same characteristic polynomial. Eigenvalues of similar matrices will also have the same geometric multiplicity. And there's a formula relating the eigenspaces. So the eigenspaces will not be the same for similar matrices. They are, however, related via the formula: the eigenspace of A for an eigenvalue lambda is equal to X times the eigenspace of B for the same eigenvalue lambda. What this means is that if you want to get the eigenspace of A, you can multiply every vector in the eigenspace of B by the matrix X that pops up in the formula for similarity here. We also have a convenient expression for matrix powers. If we want to exponentiate A to the kth power, this turns out to be the same thing as taking X times B to the K times X inverse. So this turns out to be often more efficient than simply multiplying A together a bunch of times, as long as the matrix B is easier to exponentiate in this way. So let's look at an example. So here we have an example of A and B being similar matrices. Here, A is this ugly 3x3 matrix, but this equation is telling us that A is similar to B, and B is this nice 3x3 matrix. So the fact that A is similar to B here, and B is such a nice matrix, makes A a lot easier to study. For example, the rank of B here is equal to 2. We can see that the first two columns of B are definitely not multiples of each other, but the third column is a multiple of the second. So the rank of this matrix B is 2. which automatically tells me that the rank of A is also 2, because A and B are similar, and similar matrices always have the same rank. This is nowhere near as easy to see in the matrix A, which is why it's beneficial to know that A is similar to B here. We can also see in B that the trace is equal to -3. The trace here is 0 plus 0 plus -3, which is -3. And that has to be true for the matrix A. We could calculate this ourselves by taking 74 plus -92 plus 15 and noting that that equals 3. But that calculation was easier to do on B, and we know that we'll get the same result here because these are similar matrices. I can also see in B that the determinant is equal to 0. Well, I know the determinant of B is equal to 0 because this is a lower triangular matrix, and the determinant of a lower triangular matrix is the product of the diagonal entries, and the first two diagonal entries in B are equal to 0. So the determinant here equals 0, so I automatically know that the determinant of A equals 0. The determinant calculation here, if we did it from scratch, would be a much more complicated thing for A. It's not such a complicated thing for B here. I also know the eigenvalues of B because B is lower triangular, and for a lower triangular matrix, the eigenvalues are the diagonal entries. Here, the first eigenvalue might be lambda equals 0, and for lambda equals 0, I could go ahead and calculate the geometric multiplicity, and that happens to equal 1 here. Well, I can pop back over to A, and I know that lambda equals 0 will also be an eigenvalue, and it will have the same geometric multiplicity. I also know in B that -3 is an eigenvalue, and I can calculate its geometric multiplicity, and I'll get 1. Then I can pop back over to A, and I know that -3 is also an eigenvalue, and its geometric multiplicity will equal 1. I can also calculate the characteristic polynomial of B quite easily. Remember, the characteristic polynomial is the determinant of the characteristic matrix. So that's the determinant of T times the identity minus the matrix. And since B is lower triangular, that's a very simple calculation. We end up with T squared multiplied by T plus 3. Well, similar matrices always have the same characteristic polynomial, so A has the same characteristic polynomial, T squared times T plus 3. So at this point, we know what the eigenvalues of B are. We know that the eigenvalues of B are -3 and 0. And we could go ahead and calculate the eigenspaces. So if we go find bases for the eigenspaces, this isn't terribly difficult because B is lower triangular, so the arithmetic there isn't terribly hard. And we find that for -3, the eigenspace of B is spanned by 0, 0, 1. For lambda equals 0, the eigenspace is spanned by 0, 3, 1. So we have bases for our eigenspaces of B. How do we find the eigenspaces of A? Well, we don't want to work from scratch because we want to take advantage of our similarity relation here. We know that the eigenspaces of A are x multiplied by the eigenspaces of B. Well, the eigenspace of B for lambda equals -3 is spanned by 0, 0, 1. If I multiply 0, 0, 1 by the matrix X in our factorization here, I get the vector -8, -14, -1, and that vector will span the eigenspace of A for lambda equals -3. For lambda equals 0, the story is the same. For B, that space was spanned by the single vector 0, 3, 1. To get our basis vector for the eigenspace of A, where lambda is 0, we multiply 0, 3, 1 by the matrix X that pops up in our factorization here, and that produces our single basis vector -2, -5, -1. So what this example is illustrating is that if we're given A equals X times B times X inverse, which tells us that A and B are similar, we can solve a lot of problems on B and then translate those answers back to A. And this is advantageous for us, especially when the matrix B is easy to work with.